In my last video I explained how DC motors like the one in this drill work, and in this video I'll cover a different type of motor, induction motors, like this furnace motor, or the motor in this fan, or a small shaded pole motor. This is a shaded pole motor, which is the simplest form of induction motors, and I've already taken the screws out. So let's take the rotor out, and you can see here this is a simple thing, and it's not in any way magnetic. It doesn't attract the screwdriver in any way. But it does have these lines across it, and these lines are essentially a short circuit winding on the rotor that's been cast in place. It's a bit like the rotor of a DC motor, but with all the windings shorted out. The rotor is actually passively magnetized by the stator, but these short-circuited coils here, they actually prevent the magnetic field from changing too quickly, because as the magnetic field changes, a voltage is induced that causes a current to flow, which then counteracts the change in the magnetic field. So we basically have a rotor that, even though it's very permeable to magnetism, it doesn't like its field changing very quickly. I can demonstrate the same principle with this aluminum disc. It's also like a short circuit winding. So if I put this disc between these two magnets, that induces a current in the disc as it rotates, and that counteracts it, and so it slows it down. With this shaded pole motor, if I apply DC to the coils, that creates a magnetic field which also slows down the motor. With this furnace motor, applying just a few volts DC to the stator will also slow it right down. The braking effect is enough to keep this 10-pound weight from dropping very fast. But if I cut power, it really goes. So the rotor for an induction motor really doesn't like to spin in the magnetic field. But if we spin the magnetic field, then the rotor will try to follow. Coming back to this aluminum disc, if I now move the magnetic field across the disc, that actually spins it up a little bit. So we could spin the magnetic field by spinning the stator around the rotor, but as a motor that would be very useless. So in a three-phase motor, we spin the magnetic field electrically. So imagine we have current going through the blue wires so that north is here and south is here. And next we'll apply current to the green wires and then to the red wires, and then we'll apply it in the opposite direction through the blue, through the green, and through the red, so that we have this magnetic field that keeps spinning around. In a three-phase motor, we actually apply these currents continuously as sine waves so that this transition is very smooth, and you really do get a spinning magnetic field. This spinning magnetic field will magnetize the rotor, but the short circuit windings in the rotor resist changes in the magnetic field, so as the magnetic field spins, the rotor will follow. To get this nice spinning magnetic field, we need three-phase power, but the problem is most houses aren't wired up for three-phase power. With single-phase power, all we can make is a magnetic field that goes back and forth, and on this motor I cut the starter windings, so if I power this motor up, it just sits there and hums a bit, but if I give it a slight spin, that spins it up. Now because it's only going back and forth, this motor has no preference in direction, so I can just take this motor and spin it the other way around, and it's just as happy going that way. There are many ways to give a single-phase induction motor its initial kick. The simplest of these is a shaded pole motor. In here we have two copper short-circuit windings around part of the pole, and that's what we call the shading. And as you recall, the copper winding, the short-circuit winding, doesn't like the changing magnetic field very much. So as this goes north here, the north side on here is delayed a bit, and then as it switches to south, again this part of the pole is delayed switching to south. So as the magnetic field goes back and forth, this part will always be a bit behind, and that will give the rotor its initial kick to get it going. In fact, even if I just give this motor some DC pulses, every time the shaded part is a bit behind and the rotor tries to follow to change a little bit. But now if I switch the current to AC and I get up to operating voltage, the motor runs just fine. these shaded pole windings are actually short circuit windings, and they're very inefficient. So this sort of thing is only used on very small motors. Larger motors like this furnace motor use an auxiliary winding to start up. That winding is also very inefficient, so it's always disengaged once the motor's up to speed. And as it slows down, that click you hear is the centrifugal switch turning the auxiliary winding back on. There are many different ways that are used for starting AC motors, and that could be a whole video unto itself. I'll explain more of that at the article that I'm linking from the description.